Hey everybody, welcome back to Petroleum Downstream Crash Course. Today I want to talk about the reactor designs of catalytic crackers. So in our last video, we talked about the basic concepts behind catalytic cracking, and we have also established how they work, and what can go wrong with the catalyst. Basically, we have a catalyst, and once the cracking is done, there'll be a thick layer of carbon or coke around the catalyst, and this problem is known as coking, and you'll cause deactivation of the catalyst. And furthermore, there'll be metal deposit on the catalyst. So you have nickel, vanadium, and all sorts of other metals which are sticking to your catalyst, because as the oil gets burnt or the oil cracks, there will be some deposit of metal that will be left on the catalyst, since it's not going to be the vapor. So how can we reduce this phenomenon of the coking problem? Well, for that we can investigate why it happens in the first place, and we can presume maybe during the coking process there will be a layer of oil, a few molecules of oil attaching itself to the catalyst surface. So this outside here is the oil layer, the small little oil layer that attaches itself to the catalyst. And what happens is that if it stays there too long, it will undergo thermal cracking, and all the carbon will start forming. So this will decrease yields of desired product, which is gasoline, and you increase the coking. What do you do with this? One solution is to start blowing more steam in a reactor. So if you blow steam past our catalyst particle, you're going to evaporate more of that oil, less coke is going to form, and less overcracking is going to happen. So there's less coking, and you have more of your desired products, and less metals will deposit on your catalyst as well. So our basic reactor design, let's say you have a lot of catalysts here. So you have zeolite Y powder, again 70 microns, and you have some steam, and you charge some oil inside. This can be long residue, vacuum gas oils, all that kind of stuff. You can even put short residue there, but that's going to severely affect your catalyst life for the above-mentioned reasons, because most of the metals will be trapped in the asphaltenes. Alright? So usually there'll be long residue or heavy vacuum gas oil, light vacuum gas oil, stuff like that. You can put it into your catalytic cracker, and then what happens? After a while, and the while is very short, after a while, which is 50 milliseconds and less, the whole system gets covered in coke still, even with the steam. So you've got to do something more. So what do you do about this carbon? Now some bright guy, some genius had the idea to say, hey, we can burn off the coke. Let's burn off the coke by pumping air into this reactor, burn it off, and you get CO2, and this thing will have some heat, and this heat is useful for our cracking processes, because cracking is endothermic. Endothermic means that it takes in heat. It needs heat to proceed. It absorbs heat. Alright? So you have a pump drawing in air. And then we gotta burn it off. So let's say we have this. This is our first reactor, R101, reactor 1 in area 1, or R101, and this is R102. It's like, hey man, yeah, sure. Maybe the first reactor I can have, since it's already covered in coke, I can start regenerating it. So I can send air in, I can burn off the coke, and from CO2 or CO, carbon monoxide, yeah, I can burn off my coke. Only one problem. As soon as you charge oil to the second reactor, that thing is going to be gone in another 50 milliseconds. And then say, am I going to build a third reactor? If I did that, then I'll have to wait. I'll still have to wait. And you notice you have to build thousands of reactors just to make this thing work. And if you have a continuous supply of oil, that is not going to be very practical. So you're going to need another solution. Now some guys thought, how about a continuous regenerator? So the act of burning the carbon off the coke and reactivating the catalyst is called regeneration. So what I can do is I have one reactor vessel which is there to take in my oil, and once it's covered in carbon or coke, I can send that catalyst over to a unit specifically designed to burn that catalyst, to burn all the carbon off the catalyst. So once all the carbon is burned off, this is called regenerated catalyst. And now it's ready to cycle back into my reactor so that the reaction can start again. And how do you make a powder flow? How do you make powder flow like a liquid? Flow like a liquid. This is a process known as fluidization, which basically says if I pump enough air or vapor into lots of sand or lots of powder, the thing will start to bubble and fluidize. It will start to bubble, it will start to behave like a liquid. This is known as fluidization. I have a video in the description, you can go and watch it. So what I do is I fluidize the catalyst. So I can do that with steam. And not only that, with all this heat available from burning all my carbon, I will have enough heat to actually perform my catalytic cracking. So this is how it will probably work. I will have a riser reactor specifically dedicated to do catalytic cracking. So I will have my catalyst regenerated. Excuse me. Regenerated catalyst, go from the bottom. Alright. I'll have a vaporized oil. And I'll have steam to strip the oil and also to provide for fluidization. So this is all the catalyst particles, and out will come my cracked product. Out will come some steam, and the rest will be cooked catalyst with coke on it. What they do, they send it into another reactor known as a regenerator. Alright, they're pumping air from the bottom. So in this regenerator, it's also fluidized. So pumping air from the bottom to burn the coke, and they'll get out carbon monoxide, carbon dioxide, and once it's regenerated, it goes back here. And this is much bigger than this because regeneration is going to take much longer time. So your catalyst is going to need to spend a longer time reacting or burning, getting that carbon burnt off, so that it can be regenerated. And that longer time means it needs to spend longer in the reactor, and that means you need a bigger reactor volume. So this will take anywhere, it can be from 10 to 15 minutes. This process, this will take 1 second or less. It's a very short reaction. So the second goes in, it's out. It's very fast. Now of course, there was the problem of metals depositing on the catalyst to deactivate the catalyst. So what can you do? I can draw off some of the deactivated catalyst. And I can put in new catalyst. This is known as equilibrium catalyst. Alright. So this is deactivated because of wear and tear in the reactor, the thermal attrition, thermal shock, and there'll be lots of wear and tear. There'll be attrition because all the particles are knocking against each other. So that kind of like destroys the structure of the catalyst. And there'll be metals there too, which you need to get out. So new catalyst will need to be put in, and that will help to refresh and increase the activity of the catalyst in the reactor. So that is what is called online catalyst replacement. So what you have now is an ingenious machine which is able to continuously crack the oil and produce the products you need. And of course this will be sent to a fractionator. So what are the parameters I need to control to maximize yield? Now one thing of course is the temperature of this reactor. How hot is this reactor? How hot does it need to be? Well, we have our temperature range of about 475 to 510, or even more. You can go up to 530 if you want. And so how do you achieve this temperature? Because this vaporized oil is going to come in at around 370 or so, because you don't want it to thermally crack beforehand. So how hot does this need to be? Because by the time it comes here, it's about 400 and something, 450, it could be 450, or even as low as 350. It could be around that temperature. Just note that there's a temperature drop. Can't remember the exact numbers, but there's a temperature drop. Alright, because cracking is endothermic. So how hot do you need to be? This guy here is going to be 650 to 810 degrees C. So as you burn your carbon, the temperature is going to increase to about 650 to 810. And this is because when I add catalyst to the vaporized oil, which is 370, I need to bring this guy up to around this temperature. So I cannot have catalyst at this temperature. I must have it hotter. So that will be about 650 and up. So at least I'll need a 650 degrees C in, or 650 degrees C coming out from the regenerator. So 650 degrees. So if you want to work backwards with all the heat losses, 650 to 810. So you need to jack it up maybe to 700. 700 or above, depending on how fast you need the catalyst to crack. Because temperature also increases the cracking rate. Yep. So cracking temperature is one parameter to control. And of course, the other parameter is the catalyst recycle rate. So the catalyst recycle rate will actually alter the catalyst to the oil ratio. So if you have more catalyst to oil, you're gonna have more catalytic cracking happen rather than the thermal cracking. And of course, with more catalytic cracking, you are going to have more product. But the thing is, if I cycle my oil to cycle too much of my catalyst and we don't have enough coke generation, then there's not enough heat to be produced in the generator. So that has to be controlled to maximize the yield. Now the other thing is, how often do you want to add in new catalysts? Because this is going to cost money, and that you have to do a cost-benefit analysis of how much extra product you're going to get by putting this in. So how much extra money you're going to make versus how much you spend. And moreover, you don't even have to add in just new catalysts. You can add in other stuff. You don't have to use the particular zeolite Y catalyst. You can use other kind of zeolites to alter your yield, or you can actually put in some other chemicals to trap the metals so that your catalyst will last longer. This is known as additive. Alright? And what is the pressure around here in these two? Now because you need to fluidize it, there needs to be some pressure to cause it to fluidize, to force air through the reactor bits, force air through the powder. So you are looking at around 0.5 to 2 psig. Oh, not psig, bar gauge. So this is the rough pressure you should be having inside this riser reactor for the catalytic reactor. And over here, because it's hotter and you want to circulate more air to actually ensure that the air and catalyst have maximum contact, you want to have a little higher pressure. So this is around 1 or 2 bar gauge. You don't need it too high, but you need it high enough to just let the catalyst circulate. Now, of course, this thing being larger is going to need a larger pressure difference. So we know that this is just an extra thing for you. Temperature across the various reactor systems. We have vis braking, the coil system, and the soaker system. So the soaker system will be 410 to 450 Cs. Coil is around this temperature because you need it to act faster. And in the fluid catalytic cracking process, you have about 475 to 530 or 510. It depends, but this is just a rough gauge. FCC is here. pressure, 2 to 3, oh wait no, 7 to 20 bar gauge usually. This is around, it could be less, could be more. You roughly give it around the same value as this, somewhere in the neighborhood, maybe less, because you want the cracking to be controlled. So maybe 2 to 3. Here 2 to 1 to 2 for the regenerator, 0.5 to 2 for the reactor. And the residence time, just to compare, this FCC regenerator will be 10 to 15 minutes. Visbreaker, how about Visbreaker? Visbreaker is around 5 to 15 minutes. The coil will be around 5 minutes or less. This is then the last one, the reactor itself, less than 1 second. So this 450, 475 to 530 is for the reactor. 650 to 810 regenerator, because that's where the heat's coming from. Alright, so that's just an overview. You can see the more severe temperatures, the faster the cracking goes. Alright, that's just to let you see the trend across the reaction units. Alright, thanks for watching this video. Hope you like it. Please like and subscribe if you find it useful. Thanks.